Thank you, Patrick. Thank you for being here. So if you were to take an introductory physics class, one of the first things that you would learn, are we good with the volume? I kind of feel like I'm reverberating here. One of the first things that you will learn which, should I keep going, or are we're gonna fix this? Okay. Newton's first law, anyone heard of it? Okay, so the Newton's first law, which you will learn in your early days, states that an object at rest will remain at rest, and an object in motion will remain in motion unless acted on by an outside force. And if there's a force acting on an object, it will speed up, slow down, change direction, and so on. And then the rest of your first semester will be spent solving crashingly boring problems into trying to figure out where an object is at a given time. And of course, underlying the notion of these physical calculations and mathematical descriptions of motion is the notion of the place of an object in space and the duration of an event in time. And it is very rare in those first year courses to really think carefully about what we mean by space and time. And so what I hope to do in this lecture is to, in 45 minutes, give you a brief overview of these notions as they've been considered by physicists and what our current understanding of space and time is today. So I'll begin with time. And here's St. Augustine. He knows well enough what it is, provided that nobody asks me. But if he's asked what it is and he tries to explain, he's quite baffled, which is about as good as anyone can do. Anyone here want to try to explain what time is? Anyone want to give it a go? No? It's baffling, right, when you start to think of what actually does it mean, time, right? We have a very innate physical sense of it, but what it is unclear. But we do know very well how to measure things, and we've been measuring time since the very beginning of human civilization. So obviously, first calendars were made to recognize certain cyclical and periodic recurrences of celestial objects. So much of time is derived from observations of astronomy, where we see the position of the sun change and return to its original place, whether that's from day to day or from year to year. There's a sense of time as being a continuous flow, and there are various devices like hourglasses, candles, and so on, which will mark out the flow of time as a continuous passage from the past into the future. And sometime around the 1200s or so, the first mechanical clocks were made, which utilize gravity, gears, springs, etc., to tick out even intervals of this thing called time. And so, absent a definition, we at least know how to measure things. And so we might say a day is the time it takes for the sun to return to the same position. For example, directly due south. For us, from noon to noon would be 1 day, and we can subdivide the days, and we have a second, which is, there's 60 seconds an hour, 60 hours, 60 minutes in an hour, which gives us 86,400 seconds per day. And that's the same unit of time which we define as a second now in 2019, although we define it in a quite different way. So much for time, we can measure. If we come to space, we have gone through quite an evolution in our understanding of the universe that we live in, the spatial universe. And this is an early geocentric model, which was first thought of to reflect the obvious realities that we observe, which is that the Earth is not going anywhere, right? Solid under our ground. And if we look up in the sky, we see various stuff going around. We see the moon. We see the various planets. If you can see Mercury, Venus, the sun, which goes around the Earth, obviously, Mars, Jupiter, Saturn, and so on. Up here we have the firmament of the fixed stars. So every night you go out when it's not weather like this, you see the stars rise, you see them set, but those stars don't drift around. They seem to be more or less fixed. And then way up here we have the prima mobile, the prime mover. God lives up there. Whatever sets in motion all of this is kind of located in the exterior of all of space. And this lasted for millennia because there wasn't any actual observational evidence that the Earth moved. You could explain things either way. The stars are so far away that even though they do, in fact, move around, it takes very, very precise astronomical measurements to detect this, and this motion was not, in fact, actually detected until the mid-1800s. Nonetheless, there are various schools of thought that seem to suggest that perhaps the Earth was not quite so central to our notion of space. You're familiar with Copernicus, who publishes his model of the universe that has the sun in the center, and then the planets in the order that we currently understand them to be today. Mercury, Venus, here's Earth with the moon going around to the Earth. Moon still goes around the Earth, et cetera, et cetera. But then out here, we still have the fixed stars kind of bounding space at the outer edge. And this was a much more natural way to describe celestial motions, but we still have the idea of an immovable center. Now it's the sun, and we go out for a while, and that's what we've got. But people at this time were thinking these ideas through, and so the next question to ask is, well, if the Earth isn't at the center, why should the sun be either? And maybe space simply extends in all directions. And so we have Giordano Bruno, who suggests that there's a single general space, a vast immensity which we may freely call void, in which are innumerable globes like this one on which we live and grow. So a first idea of there being other planets in the universe. The space we declare to be infinite, since neither reason, convenience, sense perception, nor nature assign to it a limit. So there you go. It just doesn't make any sense if there's an end to the universe, and so therefore there's not. So that's good. He was executed, although not for these ideas precisely. He annoyed the Catholic establishment. So building off of this idea of infinite space and the idea that the Earth, the planets, the stars, the innumerable globes are all of a similar nature, we come to Isaac Newton and his Principia Mathematica, in which he states his first law, his second, and his third law, and in which he makes various claims about the nature of space and time, with which he will go on to do his physics. And so he first addresses time. He says there's a such thing as absolute, true, and mathematical time, which flows equably without relation to anything external. So there's a thing called time. But then there's another thing which is called common time, which is measured by means of motion, such as an hour, a day, a month, and a year. So he's still carrying with him this idea that a time is a thing we measure with a clock, but that measures some ineffable, constant flow of absolute, true mathematical time. That there's some relation between what our clocks say and the single time of the universe. And he goes on to make the same claims about space. He says there is an absolute space. It remains always similar and immovable. And then we have our measure of the absolute spaces, which we determine by our position to bodies. So we can lay out meter sticks. We can do cartography. We can see where things are relative to a given map. And that's a reflection of an object space in the arena of absolute space. So this is, again, an intuitive idea. Bruno would think that made a lot of sense, and nature doesn't prohibit it. Notice there's a conception that space and time are two distinct things. That also accords with our intuition. We can move around in space all we want, but we're stuck in time going forward, and nothing we can do about that. So there's a difference in space and time. But in the meantime, we can do measurements, and then Newton goes on to do quite a lot of them. He deduces the law of universal gravitation. He invents freshman physics and all manner of other fun things. So this is basically the status of a physicist's conception of space and time through the subsequent centuries until the early 20th century. Then things change. So the sense in which things change is bound up in the nature of light. So Newton also did extensive studies in optics. He first demonstrated that white light was composed of different colors. And so we see here a prism demonstrating some of the things light does. It reflects off of surfaces, it can be bent through materials, and a prism can decompose the different colors or different wavelengths of light. This is not how Newton's contemporaries thought of light. They thought of light as they thought of colors as an admixture of lightness and darkness. So if you have white light, you have pure lightness. And what a prism does is it mixes in little bits of darkness into the white light. So if you just put a little bit of darkness in, you get red, and if you put a lot of darkness in, you get violet, and if you put all the darkness in, then you get no light at all. And this is wrong. And so what Newton did, among many other things in his optical experiments, was he ran white light through a prism to produce this spectrum, and then ran this through a prism again and recovered white light. And so this is a familiar notion to us. I think they teach it in kindergarten with the color wheel, but was not at all obvious at the time. So this notion that different colors represent different wavelengths was not one of Newton's. He thought light was corpuscular, that it came in little bits and pieces, like little bullets. That also turns out to be right, but, but I'm not going to talk about that at all in this lecture. So it is true that different colors represent different wavelengths, and the way that this was shown was by demonstrating a particular wave property of light. So next physics topic. One thing that waves do is they interfere with each other. So if you have two waves that, where their peaks line up and their troughs line up, they will add together to make one big wave, as you can see on the left-hand cartoon. And in the case where you have the peaks and troughs lined up like this, the waves will basically cancel out and you'll have nothing. And if the waves are slightly anti-aligned, then you'll get some more complicated, we don't need to, well, that's the sound of that water tank. So here you can see this demonstrated in water waves where we have two sources of waves, and you can see in here the interference pattern that the waves produce as they add up to each other or they subtract from each other. So this is an interference pattern that we can see in water waves easily with our eyes. And in the very early 19th century, Young proposed to do the same idea with light. If you have two tiny slits, the light will come through. This is a sketch of exactly the same thing. And you will see patterns of lightness and patterns of darkness where the waves are interfering with each other. And he demonstrated this experimentally. There were a lot of optics experiments at the time showing various types of wave interference. Here's a more recent example done with a laser. You may recognize these interference patterns from soap bubbles, the surface of your CDs, things like that, are all instances of those different wavelengths of visible light canceling each other out or reinforcing each other. So we have this property of light that will go on to be used to determine far more interesting things. Physical particles also do this. But I'm not going to talk about that in this lecture either. Okay, so if light is a wave, light travels with a given speed, the speed of light. Maybe it's one speed of light, maybe it's different ones. And the first idea of how to go about measuring this was proposed by Galileo in his dialogue concerning two new sciences, where one of the dialoguers asks, what kind and how great must we consider the speed of light to be? So they're generally discussing light, and they don't know, is it instantaneous? Does light actually just happen? Or does it, like other motions, require time? Does it go from point A to point B in a certain amount of time? And he wonders if he can decide this by experiment, which gives Galileo's character the chance to step in and propose one. And this is his experiment. So Galileo proposes that he's going to go up to the top of a mountain with a lantern, and he's going to train his assistant over here in very quickly opening and closing the shutter of a lantern. And he's going to send his assistant over to a different mountain. And what Galileo is going to do is he's going to open the shutter of his lantern. The light will travel over to his assistant. His assistant will see the light, very quickly open his, the light will go back, and Galileo will time how long it takes and work out the speed of light. He says he tried this. There's no evidence he actually did try it. Some learned societies in Italy at the same time did send their grad students up to attempt this. And as you can imagine, the speed of light, which we know to be actually very, very fast, it didn't work. You can't actually open the thing that fast. But the principle was sound. And in later times, people refined this notion in better ways. So one early example was Romer, who was the first person to actually get a measurement of the speed of light. And what he did was he took the distance from, this is Jupiter to Earth. This is the orbit of one of Jupiter's moons. And the moon will go behind Jupiter and come back. And this happens about a very little less than 2 days. This moon Io goes around Jupiter. And so you can time when this eclipse happens. And depending on whether you are close to Jupiter or whether you're further away from Jupiter, light will take longer to come. And so since the moon is going around once every 1.7 days, you can use the difference in timing to work out the speed of light. And he got pretty close. He got to within about 75% of the actual value this way. And then skipping forward centuries, Michelson, one of the first people to actually get close to or very near our current value of 300,000 kilometers per second, is basically doing the same idea as Galileo. He sets up an apparatus on Mount Wilson and another one on a nearby mountain in California. He has a light source that comes in, bounces off a mirror, bounces off another mirror, and he has this apparatus in here that basically allows you to very finely measure shifts in position due to the finite time it takes the light to go from here to there. So Galileo's idea was good, it's just his technology was not quite up to the task. So the speed of light was measured. It was measured to be a very large but finite value. So light, just to put this in perspective, those are very big numbers. Light travels about 1 foot in a nanosecond, about a billionth of a second it takes to go from here to here. So you are all hearing me with about a 10 to 30 nanosecond delay. So that's also hard to measure. So that said, light is a wave, visible light is. It travels at a measurable speed. And furthermore, we can determine what kind of wave light is. By we, I mean Maxwell, who was the one who actually did it. He collected all sorts of experiments that had been done in electromagnetism, and he derived his equations, Maxwell's equations, which describe how light is produced. And so to produce a light, you need some kind of charged particle that's moving around. So in our fluorescent lights here, we have electrons which are recombining with various different gas atoms. And in the process of doing, they are giving off an electromagnetic wave. So we have electric fields which oscillate. We have magnetic fields which oscillate in the other direction. And he predicted that this phenomenon should exist and that those waves should travel at the speed of light. His colleague, Heinrich Hertz, did this. He carried out the experiment. He was working in radio waves, so he produced radio waves. He detected them. He was able to measure their interference, so they were waves. He was able to measure their wavelength. He was able to measure their speed, which was the same speed as the speed of light, which had been measured by Romer and subsequent people. And having done this, someone asked him what good it was, and he says, I love this, it's of no use whatsoever. It's just an experiment that proves Maxwell was right. We have these mysterious electromagnetic waves that we cannot see, but there they are, which is the most short-sighted thing you can imagine. These are radio waves, right? This is, if you ever made a phone call, if you ever microwaved a burrito, if you ever did anything that involves remote communication, you have used this principle. So he was perhaps not the most visionary, but he was an excellent experimentalist. So we have light. It's a wave, it has wave properties, and all of this is very well and good, but there is a problem. It's aliens. It's not aliens. The problem is never aliens. Okay, so in writing this talk, I was reminded of this classic old movie poster and the tagline, if you can see it, "In space, no one can hear you scream." So promising some extraterrestrial horror there. Why can't they hear you scream in space? Who knows? Yeah. Right, exactly. There's no air. So if you're going to hear sound, there needs to be a medium through which those sound waves propagate. So through air, through water, through matter. But there needs to be something that carries that. And in the vacuum of space, there's no air. So if you're having bad things happen to you from this alien, you can scream all you like, but nobody will hear you. So this represents the physics notion, which is that if you have a wave, you have a thing that is waving. You have some medium. So you have that water that was carrying the water waves, for example. And so if light is a wave, there must be a thing that is carrying the light waves. And so this hypothetical medium was given a name. It's called the luminiferous ether. So luminiferous simply means light-bearing. Ether means it's ethereal. And so this is the hypothesis that was active at the end of the 19th century, that there is such a medium through which light travels as a wave, because we know that we can see the light from stars that are light years, hundreds of light years away. So if the light got from there to here through space, the ether must be everywhere throughout space. And given this hypothesis, you can infer certain properties of the ether. For example, it must have very low density. Why? Because the Earth and all of the other planets are moving through the ether. And if it were thick like molasses, Earth would slow down, lose energy, and crash into the sun. That has clearly not happened. And so therefore, there must be very little resistance of the Earth moving through the ether. So it would be a very low density. Nonetheless, it also would have to be under very high tension. Why? Because the speed of light is so fast. So if you consider, plucking a low tension string on a guitar, if you tighten it up, it will be at a higher frequency because it's got a higher speed. So the higher the tension of your string, the faster the wave will move. And the same thing would be true of this hypothetical light-bearing wave medium. So low density, high tension. That seems odd, but nature's odd, so okay. And it would be everywhere. So anywhere that light can get to us, there would be ether. So this room is full of ether. Okay. So Michelson, same Michelson, proposes an experiment to detect this. So he and his colleague Morley proposed this experiment, which is, we talk about great books. This is one of the great experiments of modern physics. And he proposed to use light interference. So he's going to use this property of the wave nature of light, that it interferes, in order to detect the motion of the Earth through the ether. So we have the Earth, goes around the sun, not to scale, but the Earth is moving at a pretty substantial fraction of the speed of light, not a lot, but enough so that an experimentalist of Michelson's caliber would be able to measure it. The sun may or may not be moving, but regardless of all of this motion, there is going to be some drift of the ether as the solar system is moving through space, and Earth is going through it. So since light travels through the ether and the Earth is moving in different directions, we should be able to pick up this relative motion. How? So in his daughter's memoirs, she recalls him explaining his experiment in this way. So he says, imagine that the ether drift is like a flowing river, and you're going to have a swimming race. And the way this is a pretty awful swimming race, but the way it's going to work is you're going to have one swimmer directly across and come back, and we're going to have another swimmer swimming the exact same speed, going up the same distance and back. And so the swimmer, when they're swimming upstream, will swim slower, and then when they're swimming downstream, they will swim faster than their innate swimming speed in water. And for the swimmer going cross-stream, if they're going to go directly across, they're going to have to angle them upstream a bit as the river pulls them back so that they get directly across according to the rules of the race. Who wins? I'm not going to tell you who wins, because it doesn't matter who wins. I'll tell you who wins. It's the one who goes across and back. You can work this out. I'll let you save that experiment, the calculation as an exercise for you guys. But the idea is it takes two different times. So it takes the guy going upstream and downstream longer than the guy going across and back. And so if you have a watch, you could detect this time difference, and you could figure out how fast the river is going. That's the notion. Here's the device. It's this huge, heavy table sitting in a pool of mercury to isolate it from vibrations on the ground. And the way it works, these are two diagrams showing the same thing. The light comes in, it gets split into two. Part of the light goes up to a mirror this way, that's the cross-stream swimmer. Part of the light gets sent to a mirror this way, that's the up and downstream mirror. They come back, they're recombined, and you look for them. Okay. So here is another diagram of the same thing. It gives a little more detail. There's our light source, there's the wave. And if you look at the solid one, if the Earth is not moving through the ether, the light will go cross-stream and back, upstream, downstream, and back, and it will recombine in some particular pattern. They will not necessarily be exactly in phase, but there will be some offset of the peaks of the light wave. However, if there's an ether flow, if the Earth is moving through the ether, then what's going to happen is we're going to have the light come in, and we'll have the cross stream, and we'll have the downstream, and those times will be different, just like the swimmers. And when they recombine, the waves will be out of phase or in a different phase with each other, and you could detect this difference. And he designed this horrible apparatus there such that given the speed of the Earth through the ether, he would be able to detect, no question, well out of the error bars, that he could measure the speed by looking at the interference pattern. What happened? Nothing. So, no difference, no difference. Why? Well, he said in the Michelson-Morley paper, maybe Earth was temporarily at rest in the ether. It's changing directions all the time. We don't really know which way the ether is going. So maybe it was just at rest. But they're scientists, right? They tried again a few months later, and then a few months later, they rotated the device in all different directions. No matter what they did, same result. Not so good. This held on for a long time. Maybe the Earth carries a bubble of ether with it, and that bubble is moving with respect to the rest of the ether, but it's stationary within its own kind of local bubble. And that was appealing, but turns out not to be compatible with observations of stellar positions, because those stars are still outside the ether bubble. So there's going to be a mismatch of speed which would be detectable. And these arguments are arcane and obsolete, so I shan't go into terrible detail of them. What we know now to be the case, the explanation for this is that the ether doesn't actually exist. The reason why we can't detect it is because it's not there, was not even considered by Michelson and Morley. They make no mention of this in their paper whatsoever. Because obviously the ether is there. How's light going to get through space if it's not in the ether? And more intriguingly, this guy Lorentz and some others came up with an idea that maybe the solution is that when you're moving through the ether, it compresses the objects through it. So instead of this case where the moving mirrors are moving, if these mirrors get compressed in the direction, then if they get compressed in just the right amount, then the distances will realign, so we'll get to that. And that was close, but not quite. Okay, here we are, 1903 or so. Here comes Einstein. So Einstein in 1905 writes 3 papers, each of which individually transforms a field of physics. He was 26, so get ready, get ready. Okay, this is one of them. I'm only going to talk about this one. This is his relativity paper on the electrodynamics of moving bodies, published in German. This is a translation. It's not on the nature of space and time. It's not on why the luminiferous ether doesn't need to exist. It's on electrodynamics. So he's thinking about electromagnetic waves. And he says at the beginning, it's known that Maxwell's electrodynamics, so his equations, lead to asymmetries which do not appear to be inherent in the phenomena. So basically, if you look at Maxwell's equations for something like moving a conductor in a magnetic field, which will produce a current, your equations are different for whether your conductor is moving or if your magnet is moving. But you've got the same phenomenon. And this did not sit well with him. If you've got the same phenomenon, you should have the same equations. He goes on to list some examples, and he says this kind of asymmetry in the equation, together with the unsuccessful attempts to detect the light medium, suggests that electrodynamics, as well as mechanics, possess no properties corresponding to the idea of absolute rest. So watch out, Newton, right? So whether I'm moving with respect to you or you moving with respect to me, our laws of physics are going to be the same, and so therefore, who am I to say that my space is the absolute space, or you to say your space is the absolute space? All that we can say for sure is that we're moving relative to each other. And so this, again, suggests that the same laws will be valid for all frames of reference for which the equation of mechanics hold good. This is what is known as the principle of relativity. Einstein states it as a postulate, and I summarize it here, not in his language, that the laws of physics are the same for all observers. If you're in a plane, if you're in a spaceship, if you're near a black hole, the laws of physics are the same. This is Einstein when he actually wrote it. I like to actually see him, how he looked when he did these papers, not in his wild, mad scientist stage. Okay, and then he makes a second postulate that the speed of light is constant for all observers. And this, on the one hand, comes out of the Michelson-Morley experiment, that the speed of light this way was the same as the speed of light that way, regardless of which way the Earth is moving or if the sun is moving or not. And so therefore, if the speed of light seems to be constant for all observers, let us postulate that it is. Furthermore, postulate number 2 actually comes from postulate number 1. Why? Because among the laws of physics are Maxwell's equations. What do Maxwell's equations say? That electromagnetic waves travel with the speed of light. And so if Maxwell's equations are true whether you're moving or not, then therefore the speed of light is going to be the same whether you're moving or not. So really there's only one postulate, but because this is so counterintuitive, he states it separately. Because as we imagine, you know, if you're running along a train, you will appear to be moving faster relative to the Earth than if you're just, rather to the platform, than if you're just running on the platform, right? We kind of understand that velocities are different if you're moving or if you're not. But he says no. Okay. And then here, the introduction of a luminous ether will prove to be superfluous, inasmuch as the view will not require an absolutely stationary space. So, do we need an ether? No. Do we have evidence of an ether? No. Shall we just get rid of it? Yes. Giordano Bruno would approve. Common sense makes sense. Get rid of all of these extraneous things. We're left with not really understanding how a light wave works in that case, but we move on. Okay. So this is Einstein's proposal, and now he's going to think carefully about how to measure time and space. And this is how much of a genius Einstein is. So he says he's going to define time and space. And what is time? Time is given by the position of the small hand of my watch. And so you can have a second hand on your watch as well, but time is what my watch says. No absolute time, no nothing. This is what time is. And length is length measured by my meter stick. I didn't bring a meter stick, right? So I've got a meter stick with me, and I can measure something, and I know what it is. Okay. So where's the subtlety of that? The subtlety is that we have to somehow get the speed of light to be the same for all observers. And the way that is going to work is by relaxing the requirement that there is a single time that everybody's clock measures. So if I ask all of you what time it is, you're going to pull out your phones, and those phones are all synchronized to some central time source. But if we were to see, those aliens coming by in their spaceship, and we were to ask them what the time was, their clocks may or may not register the same time as ours, and in fact they don't because of this relative motion. So how he manages to make compatible these very practical, basic definitions of space and time with the requirement that this thing, light, must have the same speed, is that time and space work differently for people who are moving relative to people who are not. And this is the summary of it. If you have a clock that is moving relative to you, it will run slower. So those aliens going by, we will see them in very slow motion because their clocks are running slow. And furthermore, moving objects are contracted in the direction of motion exactly the same amount as Lorentz proposed to solve the Michelson-Morley problem. So he was on the right track, but we have a shorter time and a shorter distance, so we can get the speed of light, the distance over time, to be the same for the moving scientists and the stationary scientists. The derivation of this, I invite you to take my physics class, and we'll do all the algebra. But in the interest of time, I'm going to skip it. So by how much does time slow down and how much the distance changes? It's given by this factor here, which was derived by Lorentz. That's the velocity of the moving observers. There's the speed of light. Here's a plot of it. And you can see that for low velocities relative to light, upwards even of 50% of the speed of light, this factor by which time changes is 1, doesn't change. So this is why you've never noticed that when you run back to your dorm room and come back to class, only a few seconds have passed, whereas class is now half over, right? Because your gamma factor is very small. But if you go out to about 87% the speed of light, the factor by which these things change is about 2. So you can see that the stationary clock has ticked off about 22 minutes since noon, the moving clock about 11 minutes since noon. So it's gone slower by a factor of 2. You say, well, this sounds good, but I don't actually believe it. So obviously we want to test this experimentally. And in the early 1940s, the first tests of this were made studying radioactive decay of very rapidly moving cosmic ray particles. And it was found that these particles that were moving at 0.98 times the speed of light lasted much longer before decaying than they should have. You say, well, maybe we don't understand cosmic rays that well. In the 1970s, they took clocks and put them on an airplane and flew them around the world and took the clocks back off and looked at their time elapsed relative to stationary clocks. And sure enough, even at a very, very low speed for an airplane, at a very high precision, which atomic clocks had reached at that time, they observed this effect happening. And since then, there have been multitudes of experiments that, again, I don't quite have time to go into, that demonstrate this effect. So there is no absolute time. There is no absolute space. And your measurement of time and your measurement of space are linked together. So there's a sense in which these things are unified. Did Einstein stop there? No. OK. So a few years later, this is his general theory. This is Einstein himself here. He's sitting in the chair of his patent office at Bern, when all of a sudden a thought occurs to him. If a person falls freely, he will not feel his own weight. Einstein was startled. When Einstein gets startled, right, you better hold on to your hat. So here's the idea, right? If you're far in space from any stars, you'll be weightless. But also, if you are in free fall, you'll be weightless. for example, the astronauts on the International Space Station, or any astronaut in orbit, is in free fall around the Earth, and they're experiencing weightlessness, just as if they were not in a gravitational field. And the opposite is the case, that if you're in a spaceship that's accelerating, you will feel weight. And that will be the same as if you're on the surface of the Earth. And he realized there is this equivalence in terms of the laws of physics. If this person drops his suitcase, it will fall to the ground with the same speed with which he drops his suitcase on Earth, providing he's accelerating at the right speed. So here's Einstein. The laws of physics are the same. So therefore, the description is the same. There's no difference between these situations. He goes on. So now he's considering one of his famous thought experiments where we have a person in an accelerating elevator. I don't think he actually used elevators in his example, who is shining photons from left to right across his laboratory there. And because of the acceleration, we will perceive these photons to travel in a curved path. And we know from all of those optics experiments of Young and Fresnel and Newton and so on, that light will take the path that minimizes its travel time. And so therefore, if light is taking a curved path, that means that it must be traveling in a curved surface. So for example, if we fly from Atlanta to Europe, we don't go straight across. We travel a great circle around the surface of the Earth because the Earth is curved. So too with light. Can we see that? Oh, yes, we can. So here's the sun. It's a great mass, and it is curving space around it in this cartoon. And if space were not curved, light would move on in a straight line, obeying Newton's first law of motion. But now it's not being acted on by an outside force. It is simply traveling in this curved space, which banks it around the sun. And so too are the planets traveling in this curved space, keeping us around the sun. And is this detectable? It is if you can find some way to blank out the sun, right? Because if you're looking at light that's coming from behind the sun, passing very close, you're going to have to block out the sun. Conveniently, there was a solar eclipse just a few years after he published this paper. Lucky, lucky. And it was not cloudy on the day of the eclipse either. And Sir Arthur Eddington led an expedition to Principe, and there was a corresponding one to South America just in case of clouds. And what they observed were the positions of stars shifted away from the sun because of this light bending effect. And since then, gravitational lensing has been found throughout the universe. Wherever you have massive things, you'll see gravitational lensing. Does this affect clocks? Yes, it does. So if we have light that is climbing out of a gravitational field, it will lose energy and have a longer wavelength and a lower frequency, which means that if you have a clock which is ticking out your seconds in some way, then if, excuse me, you have a clock that is in a gravitational field, by the time that signal gets out, it will be going slower. So a clock in a gravitational field, a strong gravitational field, will be slower than a clock that is further away. And this is the corresponding factor which describes that. There's the mass of the object, the gravitational constant, the speed of light, and the size of the object. So the sun curves space a little bit. Various exotic objects in the universe, like white dwarfs and neutron stars, are even more compact, and they curve space more. And we reach an ultimate end in the case of a black hole, where the object is so small that it forms this event horizon at a radius equal to this conglomeration of coordinates, where we have, if r is 2gm over c squared, that's 1 minus 1, which is 0, and clocks appear to come to a stop. So this is the idea that as you're entering a black hole, time will go slower and slower and slower until it stops. You will pass through the event horizon and have very, very bad things happen to you. But if you manage to stay outside of the event horizon, your clock will run very slowly compared to to your friends back home, they will age quite a bit while you age very little. I think there was a Hollywood movie about that recently. So, Dr. Bonning, you say black holes seem very unbelievable. I'm not entirely sure about that. But remember, these effects happen for any mass, for any speed. And so one place where relativity is absolutely critical to take into account is you using your phone to figure out where you are. So this is a cartoon of the GPS satellites. And as you can see, the GPS satellites are moving relative to the surface of the Earth. And so therefore, we expect their clocks to run slow by about 7 microseconds per day when we calculate this. But they're also far away from the surface of the Earth. So our clocks are running slower relative to the satellite clocks. And the difference is that the clocks above the Earth run fast by 45 microseconds per day. And so the total is that these clocks are running 38,000 nanoseconds per day faster than the clocks on Earth. How do GPS satellites work? It's complicated, but they're basically sending signals to each other and triangulating by light travel time between the satellites and your phone, for example, where your position is. And so if every day these clocks drift by 38,000 nanoseconds, remember 1 nanosecond is a foot, your location is going to drift by 7 miles per day, which is bad if you're trying to get somewhere. So this is absolutely known. In fact, it's calculated even with more precision, considering the Earth is not actually a perfect sphere. And the way they account for it is when they construct these clocks in the manufacturing facility, they will design them to run slow so that when they're in space and they speed up, they will be synchronized with our clocks on Earth. So that is an actual very real application of relativity of both kinds, which simply would not be possible without these understanding of how space and matter in space affect time and how they are linked. Okay, 2 minutes, super quick, because this is super exciting. Okay, if this is the case, then we can also produce waves in space itself. So never mind the ether. Ether doesn't exist, but space itself has structure. It's not a thing in space, it's space-time. And if we have moving gravitational charges, just like our electromagnetic waves, they are going to curve space. They're basically going to stir it up like a big pot of molasses or something, and these waves of space-time curvature are going to carry off vast amounts of energy from some merging object. So, quite frankly, you spinning around, in your dorm room will produce gravitational radiation. No one will notice it. But if you have white dwarfs or neutron stars or black holes, something that has intense space-time curvature, then you will, in principle, produce a detectable signal. And have we detected them? Yes. How? By using Michelson interferometers. We're back where we began. So these are enormous Michelson interferometers. These arms here are about 4 kilometers long. The same idea, light comes in, comes off, bounces off the other end. Here's a cartoon of how it works. That's going to run, hopefully. There it goes. There comes the light. It's split. It recombines. And there are the mirrors. They're moving. Why are they moving? Because the space that they are in is shifting. It's oscillating because of these gravitational waves. These are the light waves of an infrared laser. Bounces off the mirror, comes back. The simulation is from LIGO, the observatory I showed you. They'll recombine. You see we've got destructive interference. They're going to cancel each other out. But as the gravitational wave comes through, we will see these shifting patterns of interference, and we will infer these changes in space itself. These changes are of the size about a fraction of a proton. So although gravitational waves are drifting through this room at this very moment, we don't actually notice them. It took decades of technology development to produce these, and in 2015, the first such signal was detected. Here's before the collision. There's the strong gravitational wave, and then it comes out. the measurement is 1 part in 10 to the minus 21, and here's the little chirp of the merger. So we have now detected waves of space-time curvature, and it's become a new field of astronomy. And if you ask the Hertzes of today, what use is it, they will say, well, I don't know, I guess it proves Einstein, right? But we have no idea, right? We have no idea where this is going. We are just in the beginning stage. And so I'm running out of time. I want to take questions, but I thought I would just leave you with the official internationally agreed definition of time and space. The definition of a second is this many periods of radiation corresponding to the transition to hyperfine levels. This basically adds up to 1/86,400th of a mean solar day. And then the length of a meter is determined by defining the speed of light to be constant, and so therefore how far light gets in this amount of a second, which is a meter, is the definition of a meter. So now you have the answers to what are time and space, and I thank you, and I will take questions.
Are there only 2 Michelson measurement places like that?
There are a handful. So there is one that is there are 2 in the US because you want to make sure that both of them detect the thing. There is one called Virgo in Italy. There are some smaller ones in Germany and Japan. You can imagine Japan vibrates a lot. So these are more kind of technology development centers. India is building one. So yeah, eventually there will be a kind of worldwide network of them. Right, so the basic idea is we want to be able to triangulate where these signals are so we can look and see what's going on. If you only have 2, you're basically limited to it's in that direction of the sky. So yeah, that's.
So when you were discussing how objects would move through time faster as they speed it up, and the equation you used was based off the speed of light, but the equation would fail when an object reached the speed of light. So what would happen if
Yeah. So you've heard the speed of light is, the ultimate limiting velocity, and that comes out of this derivation of how time and space have to be altered in moving systems in order for the speed of light to be constant. And yes, so at the point where your velocity is equal to c, you have 1/0, and all of these things blow up. And so this is why things cannot reach the speed of light, except for light, which is a different sort of thing. So it's kind of a demonstration of the fact that you can't reach it. And if you have a velocity that's greater than the speed of light, you've got a square root of a negative number in there. And what does imaginary time mean? I mean, there's theorists who've got ideas about imaginary time, but that's just not in classical physics, that's not a sensible thing. Yeah, so that's why you can't go faster than the speed of light. Yeah?
So then basically is that what the case that we're 1/0, then we see no time?
Yes, so in a sense, not a very good sense, but from our point of view, light travels from here to there with a finite speed. If we were a photon, the photon, in a sense, all of space is contracted to a point, and all of time is now. So that's kind of, right? That's not really a good way to think about physics if you're going to do some physics calculations, but going along what you were asking, if you were to kind of take the math to its conclusion, that's what you might infer for the nature of a photon. So a photon just being very different than a massive particle in all these different ways, yeah. Yeah?
What's the role of dark matter when it comes to space and gravitational waves?
Good question. So dark matter is matter that we cannot see. So a black hole is a type of dark matter because it doesn't give off light, but we know that there is another kind of matter. It's pervasive in the galaxy. It shows up in clusters of galaxies that produces a gravitational field that we can't account for by other things. So as it is a mass, it would curve space, and part of the evidence for dark matter is that we see light bending around clusters of galaxies in such a way that it requires more mass there than we can see, and so therefore dark matter is there. So we do see it in terms of light bending. In terms of gravitational waves, except insofar as black holes are a type of dark matter. Dark matter clumps, such as we expect to see in dwarf galaxies or so on, they are still quite large, and so their gravitational field is relatively weak, so their amount of curvature is low. So we don't expect to see, if we see a dwarf galaxy being consumed by a larger galaxy, we wouldn't expect to see gravitational waves from that. But we do see the light bending. Ah, yeah.
So dark matter, isn't again particle?
We don't know. We don't know. There are theories that hypothesize different types of particles that act like dark matter, and there are experiments that are ongoing in universities and national labs attempting to detect these hypothesized particles, and they haven't done it yet. So we're not in an ether stage yet. We don't need to dispense with dark matter entirely. We're still in this stage. We're in the Galileo with his lantern stage, that we really don't have a very good idea, and so we're just trying something, and we're kind of, by we I mean the scientific community, is refining their measurements. Yeah, so that's coming, but we'll see.
Like free fall, is that like a type of deceleration movement?
Free fall is like acceleration. So you're accelerating down, but you don't feel a weight when you're in free fall. Yeah.
So what would the effects of gravitational waves like appear much closer to the source?
Yes. So gravitational waves do this. So if these were, a bunch of test masses, just a ring of masses floating in space, and a gravitational wave came through the screen, then it would squish this way and that way. So that's what we see. So that's hence why the Michelson interferometer is a good instrument to detect this, because you put a mass here and a mass here, and their relative distance changes, so you can pick up the interference. So yeah, that's what the gravitational waves look like. And again, the actual change is really minuscule. Yeah.
Is it possible that dark matter is like the ether,
In
in the sense that it's just a useful hypothesis until we understand something better, and then we might eventually be able to dispense with that?
It is possible. There is a coterie of physicists who are pursuing this idea, the idea being that just like, I'm sorry, these gravitational waves are bothering me. Let me, there we go. Oh, we'll bring out this. Okay. So just like relativistic effects don't show up until you're going very fast, but we don't see them when we're going slow. We don't see general relativistic effects when the gravitational field is weak. So the idea is maybe on big scales, on galactic scales and galactic cluster scales, we don't understand gravity. And this is known as modified Newtonian gravity, modified gravity. There are some observations which are not quite consistent with that, but that's an idea that people are pursuing, which would be, yes, it's not that there's some mysterious matter, we don't know what it is, it's that we don't understand the laws of physics at these large scales well enough. It hasn't got a lot of traction because of these observations that it can't explain, but there's definitely this idea that possibly it is ether-like in that sense. One more? Is it quick? We'll see.
So if there were such a thing as time travel, how would it work? You seem to be pretty good at measuring space.
I can't tell. That's a good question. So how it would work. All right, so we have space-time. We have 3 dimensions of space and time that are linked together, and this continuum of space and time can be affected by the presence of mass. And so we can imagine, for example, taking this bit of space and yanking it over here and connecting it to that bit of space, which would be like a wormhole, which we see in science fiction. Or we could take this little bit of time here and link it back into the past so that we could prevent World War II or something. So these would be changing the structures of the geometry of space and time. That's how it would be done. how you actually do that, we have no idea, because we know how matter works. We don't even know how dark matter works. How to manipulate the structure of space-time deliberately in order to affect these travels to different times or different places, it's still science fiction. But that's a general notion of how you'd go about doing it. If you have an idea, let me know. We'll talk about it. But I think we have to finish.